speaker this morning is Saša Popović, who has tasked for us what remains to be done, prospects for future historiographical research. So look forward to it.
Thank you, Deborah. Thank you very much. I would like to thank, of course, the Isaac Newton Institute for hosting this wonderful event for the past several months, actually, and of course, a big thank you to the organizers for putting this up. It's really a pleasure and an honor to be here and to be speaking about something that is very dear to my heart, that is Giuseppe Veronese, the Italian mathematician, late 19th century pioneer of non-Archimedean mathematics, but whose results in non-Archimedean geometry are, I would say, much less well known than his results, for instance, in projective or algebraic geometry from the 1870s and the 1880s. Now, the title is Veronese Lives Again, and a rewriting of the history of Fin-de-Siècle non-Archimedean mathematics. And whenever I speak about Veronese, I like to begin with this. This is a quote from Rodolfo Betazzi, also one of the participants of these discussions concerning the status of infinitesimals in mathematics in the late 1900s. He said in this article on actual infinitesimals published in Peano's Rivista di Matematica, our goal is to promote a change of perspective on such an interesting subject. And here you can see his very important book, Teoria delle Grandezze, in which he approached the question of founding non-Archimedean mathematics from, let's say, an algebraic point of view. So he was quite influential at the time. Also not that well known today, I would say. So now the question is, of course, how does one start working on Veronese in the first place, and why actually Veronese? And then a methodological question, how are we to approach this study? And this also is an interesting thing. When you ask the ChatGPT, who is Veronese? Well, he will tell you that he is not a widely recognized figure, and that there may be individuals by that name, but without further context, it is hard to determine who specifically you're referring to. I have to say that in the meantime, ChatGPT advanced, so now he will tell you something about Veronese's results in algebraic and projective geometry, not so much about these results, which I shall be mentioning today concerning non-Archimedean geometry. So, who was Veronese? Well, he was, at the time, an internationally renowned authority on projective and algebraic geometry. Some of these results we mentioned yesterday during coffee time. For instance, Damien immediately said, oh, well, of course, the Veronese embedding, the Veronese surface, these are these famous results. Also geometry of hyperspaces, so n-dimensional geometry, non-Euclidean geometries as well, and of course, the most important for my talk is the non-Archimedean geometry, which he introduced in 1889 in a paper concerning the axiom of continuity, in which he tried to see whether we can speak about continuity and, in a way, separate this talk from talk about Archimedicity. So to propose a condition of continuity, which is a non-Archimedean one, and then he publishes his main book, Fondamenti di Geometria, in 1891, and then elaborates these ideas concerning non-Archimedean geometry up until 1909. Now, he's also interesting because in this very big book, Fondamenti di Geometria, and also in subsequent titles such as the Elementi, which is a condensed version of the first one, he worked on the foundations of mathematics, of course. He worked on the history of mathematics as well. He had a keen, let's say, historical acumen, and this is evidenced by the appendix to the Fondamenti, which contains a historical and critical overview of all the attempts concerning the foundations and principles of geometry. And interestingly, ever since he worked with Wilhelm Fiedler in Zurich, he was interested in mathematics education, and in 1883, it was thanks to his initiative that Italy received his first ever center for building mathematical models, which ought to be used in teaching, especially students. So these are the relevant publications. So from, say, 1876 to 1883, we have a number of original contributions to algebraic and projective geometry, and then from 1889 to 1909, a series of papers devoted to non-Archimedean geometry. Now, one of the issues when one is working on Veronese is that most of these papers are very hard to find, so they haven't been digitalized prior, but I've managed to do so in the meantime. So thanks to the help of my colleagues from the Mathematical Institute in Belgrade, and thanks to a grant I've received from the International Commission on the History of Mathematics, a big thanks to June and all other members of the ICHM, I've managed to compile this digital repository of Veronese's works. So they're all available online now, so whoever wants to read through them, work on them, they will be able to find them on this link at the website of the Mathematical Institute in Belgrade. So this is the fundamenti, so foundations of a multi-dimensional geometry, and the geometry which introduces what he calls più specie di unità rettilinee. These are actually the non-Archimedean linear continua, so infinitesimally enriched continua, which he introduces in his geometry. And the most important part, I would say, is this introduction, which is very long, almost 100 pages, concerning the fundamental principles of abstract mathematical forms, and also this first part concerning the straight line, the plane, and the space of 3 dimensions within the so-called general geometrical space. I really liked these, let's say, methodological prescripts found in Veronese's appendix to the Fundamenti concerning the way in which we should approach the history of mathematics. So he advocated a kind of a critical approach to history, saying that impartiality must always go above every other sentiment, above all other personal considerations. The critique should be incisive, calm, mindful, and charitable, con l'animo verso il bene. And it is necessary to get rid of all prejudices, for in all parts of mathematics they are nowhere as deeply rooted as in the case of foundations, where the thoughts of others are easily travestied, be it because of the opacity of style of numerous notable authors, or still as a result of a careless and superficial critique. And now I will try to show that people who were working on Veronese starting at the late 1900s, early 20th century, were not following these methodological prescripts whilst reading his papers and his books. And we've arrived at a... Cassira, yes?
Where does he say that?
He says it, I'll have the reference in a moment, so I'll mention it. So my project is, I'm especially interested in this reception history of Veronese's theory, which I think is quite peculiar, because initially it was discussed by leading mathematicians, starting from Veronese's Professor Cremona, then Felix Klein, Schoenflies, Cantor, Killing, Peirce, Poincaré, Hobson, Pieri, Fano, so very great mathematicians. Hilbert, in his Grundlagen der Geometrie, refers only to Felix Klein and to Veronese's book on the foundations of geometry as the most important ones for his own work. Theodor Fallen, who we mentioned yesterday in Norbert's talk, also in his book Abstrakte Geometrie, in a footnote mentions that when it comes to my approach to the foundations of geometry, one should look at Veronese's book. So he was also leaning upon Veronese's work. Also, his works were presented in leading journals, for instance, in the Jahrbuch. An interesting historical, I'd say, piece of information is that Ernst Köther's review of Veronese's Fundamenti was 13 pages long. So this set truly a precedent for the Jahrbuch. It is, I believe, the longest ever review of a book. He found it to be absolutely of fundamental importance. For comparison, other papers devoted and books devoted to the foundations of geometry, for instance, by Sophus Lee, by Poincaré, by, I believe, some of the Italian mathematicians, received no more than 3 or 4 sentences. So Veronese was considered very, very important. Also, great many articles in the Enzyklopädie, Klein's Enzyklopädie der Mathematischen Wissenschaften, also contain numerous references to Veronese, especially Enriquez's great paper on non-Archimedean mathematics. Also, a thing that is very interesting to me, because I'm also someone who studied philosophy, is that Veronese's non-Archimedean geometry quickly garnered the attention of philosophers working on the foundations of mathematics. And this is quite interesting because a Belgrade philosopher, Branislav Petronijević, was also an associate of the Mathematical Institute where I work now, was actually the first person to really systematically study Veronese's works at the beginning of the 20th century. And exceptionally important is this study from 1907, the Typischen Geometrien und das Unendliche, published in Heidelberg, in which he conducted a systematic comparative analysis from a historical point of view, but also a mathematical point of view, of the theories of infinite numbers provided by Cantor and the ones introduced by Veronese in his book Fundamenti as a sort of arithmetical model of the axioms of non-Archimedean geometry. Also, a very important article on Fontenelle's infinite numbers was published by the Accademia dei Lincei on Veronese's suggestion, and the paper was communicated to the members of the Academy by Tullio Levi-Civita, who also worked on Veronese's non-Archimedean geometry and actually provided the first analytical model of Veronese's geometrical axioms. So this is an excerpt from Petronijević's autobiographical note, where he says that Veronese considered him one of only a handful of people who properly understood his theory at the time. And he also mentions that while he was writing the Die typischen Geometrien, he could not completely understand the relationship between Veronese's numbers, so these new sorts of infinite numbers that were introduced by Veronese, and his non-Archimedean geometry. And he adds, which was first introduced and invented by Veronese and then later reinvented by Hilbert, nor could Poincaré, interestingly, I'll be mentioning Poincaré later in this connection, nor could Poincaré help me by explaining any more clearly. I finally managed to grasp it on my own somewhat later. And he also goes on to add, this is also quite, I believe, interesting from a historical point of view, that during his 2 stays in Rome, he got to personally meet Veronese, and he learned Italian sufficiently well by then, so he could reread Veronese again in Italian, so in the original. And in one of the conversations they had, he suggested to Veronese that it would be good to write a shorter, more condensed work in which he would expound in a clearer and shorter form all of his principal results concerning the theory of infinite numbers and non-Archimedean geometry. And the unfortunate thing was that Veronese passed in 1917, so as Veronese adds, this book never seemed to have been published, since Veronese died shortly thereafter. But one interesting thing is that I've managed to find this note that was written by Veronese himself, a marginal note on the manuscript of the 1917 publication for the Accademia dei Lincei, which reads something of the sort, had I known about Mr. Petroniewicz's result in this field beforehand, I would have done some things differently when it comes to my own theory. So he really did consider Petroniewicz a very important connoisseur of his work. Now, when it comes to the Neo-Kantians, here it is, Cassirer and the others. So following Petroniewicz, we have the Neo-Kantian philosophers of mathematics getting interested in Veronese's book. Of course, they were beforehand interested also in non-Euclidean geometries, so it was in a way natural to now go and investigate a new non-geometry, so non-Archimedean geometry. We have Gawronski in his Habilitationsschrift, Cassirer in the Substanzbegriff und Funktionsbegriff of 1910. That's where the quotation is from. And Nathrop in the Logical Foundations of Exact Sciences. Also, they were interested in defending Hermann Cohen's controversial book concerning the infinitesimal calculus and the infinitesimal method. So they tried to rely on Veronese in order to help Cohen react to those criticisms by, say, Cantor or by Bertrand Russell and many others. And also, Joseph Bloch should be mentioned. He wrote this book on the development of the notion of infinity from Kant to Hermann Cohen, where he also mentions Veronese. Now, since we are at Cambridge, I found it natural to mention Veronese's reception here. So I'll focus on these 5, sorry. Arthur Cayley, Herbert William Richmond, Ernst William Hobson, Bertrand Russell, and John Conway. Now, when it comes to Cayley, these connections between Cayley and Veronese have been covered in a paper by June Barry-Green and Jeremy Gray concerning the geometry, the development of geometry at Cambridge from 1863 to 1940. And it is interesting that some of Veronese's results from the 1880s actually can be connected with Cayley's ideas concerning configurations obtained by sections and projections of a given projective space. And this was noted already by Walter B. Carver in a 1905 paper on the Cayley-Veronese class of configurations. And it is quite interesting that Veronese himself was, of course, familiar with Cayley's work, and he mentions in one of the letters to Fiedler that his approach differs from Cayley's because it is purely geometric, whereas Cayley's, he adds, much like Riemann's, is nothing but pure mathematical analysis. Now, when it comes to Richmond, he was especially fascinated by Veronese's work on Pascal's mystical hexagram, so Pascal's theorem in projective geometry, and he wrote practically 2 reports on Veronese's paper, one in 1900 and one before that in the Transactions of the Cambridge Philosophical Society in 1894, and he goes on to speak about Veronese properties of Pascal's hexagram. He believed that Veronese extended the results of other authors working on the field, so people like Steiner, Plücker, Cayley, Harman, Kirkman, and many others. When it comes to Hobson, he mentions Veronese already in his presidential address to the London Mathematical Society, titled On the Infinite and Infinitesimal in Mathematical Analysis, mentions Veronese's book, which was already controversial at the time, so the matter was subject to considerable controversy. But he adds that one of the most interesting results on the speculative side of abstract science, which has been obtained in the 19th century, is that it is possible to set up two or more conceptual systems which are each self-consistent but contradictory with one another. So to Hobson, it was obvious that we can have alternative systems in geometry or in other mathematical disciplines, each of which can be consistent, but they needn't be complementary in a way. So another reference to Veronese in Hobson is to be found in his The Theory of Functions of a Real Variable, where he mentions that Veronese was one of the constructors of these abstract theories of measurable quantity, refers to Veronese's book, and adds that if space is to be regarded as made up of elements, these elements must themselves possess spatial character, and this view has given rise to various theories of infinitesimals or of indivisibles as components of spatial magnitude. The most modern and complete theory of this kind has been developed by Veronese in his Fondamenti, and is based upon a denial on the principle of Archimedes. Now, Russell is also very interesting because at first, during the earlier stages of his career, where he was still working on mathematics, he was especially interested in geometry, and he mentions the Italian geometers in a paper that was unpublished, but it can be found in Russell's archive in McMaster, recent Italian work on the foundations of mathematics, where he says that Italians, in Italians we find a clearness of distinction, an accuracy of definition, and a rigor of demonstration such as rarely be met with elsewhere. And also in his Encyclopedia Britannica entry on non-Euclidean geometries, he lists Veronese's Fondamenti among the most important works, as he says, for a study of non-Euclidean geometries as well. So we have really a combination of various approaches in this one book by Veronese. Also, in his dissertation, an essay on the foundations of geometry, he goes on to refer to Veronese's book numerous times. But interestingly, this, let's say, initial positive reaction changes to a mostly negative one, I believe, through Russell's study of the works of German mathematicians, most notably Weierstrass, Dedekind, and Cantor, and he goes on to write this report, recent work on the principles of mathematics, in which he formulates a certain anti-infinitesimalist stance, so a critical attitude towards non-Archimedean mathematics in general. I will mention this somewhat later. But it is interesting also to note that Philip Jourdain, in his review of this report by Russell, adds that Russell's profoundly anti-historical perspective reveals itself in a rather unfortunate way in his inaccurate and superficial remarks. And finally, the late John Horton Conway, mathematician here at Cambridge and then later at Princeton University, who is of course best known for his book on numbers and games, I believe, and for the so-called theory of surreal numbers, which is one of these contemporary non-Archimedean theories, which in a way has certain connections with the late 19th, early 20th century ones. He also worked, interestingly, on these earlier papers by Veronese on his own work on the Pascal hexagram and the Pascal theorem in projective geometry, but he ran into Veronese's paper by accident because himself and Riba were reading an 1879 paper by Christine Ladd, the Pascal hexagram published by the American Journal of Mathematics, who attributed most of the results they themselves have arrived to Veronese. So Conway goes on to say that they hope this paper will encourage other explorers. So go study history, you will find numerous interesting things there. And when it comes to this connection with, between Veronese's theory and the theory of surreal numbers, Philipp Ehrlich, one of the people who have been working most intensively on the history of non-Archimedean mathematics, says at one point that the theory of the rectilinear continua developed in Veronese's Fondamenti is a profound and relatively sophisticated theme of whose central concepts and ideas permeate the 20th century theory of ordered algebraic systems, and through it, even the theory of surreal numbers. But
Could you say a couple of words the Pascal hexagram?
Yes. So this is the Pascal's theorem from projective geometry. So these are these configurations of points, lines, and so forth. I mean, it's quite complicated to explain it in a couple of minutes, so I'd rather skip that. And
it's an intersection. It's the result of an intersection.
Intersections, yes, exactly. So the problem is, shortly after this initial burst of enthusiasm for Veronese's work and for Veronese's new geometry, practically after Veronese's death, at the beginning of the 1920s, we can see that discussions in mathematical but also in philosophical journals alike have shifted to other mathematical subjects, notably arithmetic, set theory, and logic, and consequently to other authors. resulting in a peculiar situation that Veronese's results, especially these concerning non-Archimedean mathematics, seem to be almost entirely unknown by contemporary mathematicians, philosophers, and historians of mathematics alike. So this striking asymmetry in the initial and final stages of the reception of Veronese's theory is what I'm most interested in and what my practically PhD thesis is devoted to. So hence this motto, promoting a change of perspective on an interesting subject. Now, a few words about the methodology. Some things will coincide with the things that have been said here yesterday. So this is, of course, one of the most important, I think, periods in mathematics. So this modernization period, as Nicolas Michel said yesterday, so the modernist transformation of mathematics, which happened from the 1890s to the 1920s or 30s, and this famous publication, of course, first by Herbert Mertens, and then these two works by Jeremy Gray, in which he focuses on this modernist transformation, how it came about, and so forth. And one of the key ideas here is that these radical innovations that happened were of a conceptually transformative rather than linear cumulative development. So the question is, of course, then how should we approach the study of the history of modern mathematics? And should we look at it just as some clash between the moderns and the counter-moderns, as Mertens wanted to describe it? So I think that the key insight here, and I take this from Ferreiros and Gray's The Architecture of Modern Mathematics from 2006, is that the history of modern mathematics provides opportunity for realizing that many pivotal mathematical contributions were not philosophically neutral, and that great mathematicians have concerned themselves with eminently philosophical questions. In other words, they were philosophizing mathematicians, and then this, I think, allows us to be more open-minded and to, I guess, work on more open-ended and flexible interpretative schemes, and as they mentioned in their paper from 2022, Jenny Boucard, she will be talking about this later on. So this mélange des genres, mixing various different approaches and perspectives in order to arrive at the best possible explanation of a given and an analysis of a given historical period. Now, when it comes to this modern history and philosophy of mathematics, this integral approach, at first, of course, we had within the history of mathematics this clash between the internal and the external approaches to history. On the side of philosophy of mathematics, also, we had these typically ahistorical foundational studies at first, and then we have this newer, practice-oriented and more historically informed philosophy of mathematics, which takes into considerations these novel historical case studies, and as it says here, we have this interest in broadening the perspective of philosophy of mathematics so that it engages historical case studies. The new focus on the history of mathematical practice emphasizes precisely how such practice is intertwined with philosophical ideas. And I believe that we find exactly this in Veronese's opus. So I propose that we use this integrated historical-philosophical approach, as Jeremy Gray goes to say, that great mathematicians were behaving like philosophers of mathematics, and we need to be both historians and philosophers to see it. Interestingly, Petronijević, whom I mentioned in the beginning, advocated this kind of approach in the early 1900s because he was also very much interested in the foundations of mathematics. He worked on it, but he also was interested in parallel in the history of mathematics, and he says explicitly that his papers on the history of mathematics are intimately connected with his research into the logical foundations of mathematics. So he wrote on Veronese, he wrote on the founders of non-Euclidean geometries as well, on Cantor, and many, many others. Now, one thing that we've been mentioning before the talk actually started are these alternative or competing accounts of the historical development of non-Archimedean mathematics. Namely, many modern accounts of non-Archimedean or infinitesimal mathematics typically tend to focus on the development of the calculus and mathematical analysis, and less so on the role of infinitesimals in geometry or the so-called theory of magnitudes. So that is why I propose that we should look more broadly into the history of geometry and into the history of algebra while trying to analyze and reconstruct and write, in a way, this history of Fin-de-Siècle non-Archimedean mathematics. Because the ideas of Veronese, they permeated not only geometry, but they were also then adapted and transformed within set theory, within logic, within algebra, and I believe it is possible to find a sort of a continuous thread which binds these ideas together, and then we can follow it and then piecemeal reconstruct this development. Now, there is also one problem that there are authors who work on the history of non-Archimedean mathematics and who tend to make these leaps from, say, Leibniz and late 17th century infinitesimal analysis to 20th century advances such as non-standard analysis, smooth infinitesimal analysis, etc. And such leaps are oftentimes corroborated by claims that only these more recent developments allow us to work with infinitesimals consistently and in a rigorous way. But I believe that it can be shown that Veronese and people like Stolz, Dubois-Reymond, and others worked with infinitesimals consistently as well, and that we needn't use these later theories to read the historical papers and books from the 1890s, say. So we have the Robinsonians. This started with Robinson himself in a way, though, where he says that it might be appropriate to conclude his book on non-standard analysis with a number of remarks which attempt to indicate the ways in which this prevailing picture of the history of the calculus should be supplemented or redrawn. And then Lakatos, of course, is a classical example of someone who accepted this usage of non-standard analysis as a possible guide for historical scholarship as well, and for as a powerful tool for, let's say, lifting the older infinitesimal theories from the status of pre-scientific gibberish, as he says. So in contemporary terms, we have the work of Michael Katz and many other authors, Piotr Blaszczyk and so forth. For instance, this is one of the represented papers, his Mathematical History Written by the Victors, and they do work on this so-called non-standard analytical standpoint, so using these later theories in order to interpret the earlier ones. So this is somewhat of an ahistorical perspective. On the other hand, we have the anti-Robinsonians, and of course this clash with Katz and others, so this paper, A Question of Fundamental Methodology, that was actually written by many of the people who participated at this very workshop. And I will quote Craig Fraser here, who tells us in his paper on non-standard analysis, infinitesimals, and the history of the calculus, that Robinson believed that it was necessary to redraw the older history in terms or in light of the rehabilitation of infinitesimals entailed by the NSA. However, NSA and other non-Archimedean versions of calculus emerged only fairly recently in somewhat abstruse mathematical settings that bear little connection to the historical developments 1.5, 2, or 3 centuries earlier. So I believe when we are working on the history of the development of non-Archimedean mathematics in the Fin-de-Siècle period, that we should focus actually on the lacunarity, and this was the topic of the first conference that opened this research program, so that we should take this Fin-de-Siècle period seriously as a crucial formative phase in the historical development of modern non-Archimedean mathematics, because it was exactly during this period that there emerged a large and thematically diverse, technically sophisticated, and from a foundational and philosophical point of view, quite profound body of consistent and non-Archimedean mathematics, which then laid the groundwork for much of the later 20th century developments. And I believe that then we can try to retrace this development through Omega calculus, non-standard analysis, and all these other more contemporary theories. And Ivan mentioned this yesterday, and I find it quite interestingly. Of course, we have to bear in mind this fact that some statements might be analogical between the older and the newer theories. However, the methods need not be. So when looking at it, we also have to pay attention to the settings in which these non-Archimedean theories were developed. So some of them were developed within geometrical settings, some within, let's say, more algebraic setting, others within the setting of mathematical analysis. So for instance, the work on the rates of growth of real functions, etc. So, but the key thing, I believe, is this insight that truly a new impetus in the modern investigations of an adequate notion of infinitesimals was given by Veronese's book, and that this was then followed by Levi-Civita, Hans Hahn, and Hilbert. So Veronese was the chief modern champion, and this is why we should focus upon him. However, we have this unfortunate circumstance that Veronese is also a telling example of what it means to be really forgotten, even in one's own country. So when we mentioned the so-called Italian school of geometry, people were more often think of other names than Veronese's for whatever reason. So one of the things that was problematic, of course, was that Hilbert's Grundlagen could be read, as Victor Pambuchan mentions, without historical guidance, whereas Veronese's book cannot. So we need to be, as historians of mathematics, to give give him a bit of a help, in a way. And I think that Veronese himself was aware of this, because in his ICM lecture of 1908, he came to realize the extent of the difficulties with which new mathematical ideas are faced when they clash with the old and deeply rooted convictions reinforced by the authority of eminent mathematicians. And on the other side, there are also the philosophers who contribute to the obscurement of the nascent light of new mathematical truths by firmly adhering to mathematical principles they have already learned, and not realizing that these new mathematical facts, as Veronese called them, may be beneficial not only to mathematics but also to philosophy. So now the dramatis personae, so to say, or the cast of a historical drama. On the left-hand side are the people who worked on non-Archimedean mathematics and the people who supported them, whereas Veronese here is a key figure, I would say. And on the right-hand side, we have the people who are either against infinitesimals or people who worked on non-Archimedean mathematics, for instance, like Hilbert and Dane, but who approached a different style of approach and different, let's say, methodology. The three gentlemen here, Stolz, Dubois Raymond, and Johannes Thoma, before Veronese, they worked on infinitesimals. However, they did not work on it in a, I would say, in a systematical fashion. Stolz produced several papers which are quite historically oriented, devoted to Bolzano's contributions to the history of analysis, also to the Archimedean axiom. He analyzed various formulations of the Archimedean axiom and so forth. And then Dubois Raymond and Thoma have been working on these infinitesimals in the context of the ratios of growths of real functions. And interestingly, Dubois Raymond also wrote a book, Die allgemeine Funktionentheorie, Metaphysik der mathematischen Grundbegriffe, so metaphysics of basic mathematical notions, which is really a philosophical book devoted to philosophy and foundations of mathematics, in which he espoused similar ideas to those of Veronese. On the Italian side, this trio, Bertazzi, Veronese, and Levi-Civita, and I especially want to mention these two papers by Levi-Civita, which are not that well known, because people will typically associate Levi-Civita's name with the Calcolo Assoluto, so the tensor calculus, which he worked on with Ricci, or his work in mechanics or physics. But these two papers are in non-Archimedean mathematics, so the first one in which he provides an analytical model of Veronese's axiom of geometry and actually introduces the so-called Levi-Civita non-Archimedean ordered field, and then another paper on transfinite numbers in which he further elaborates these ideas. Interestingly, this first paper was written, very important one, whilst Levi-Civita was still a student, so he was studying under Veronese and under Ricci in Padua. And these four people here, Cantor, Peano, Russell, and Poincaré, I think are the main culprits, so to say, for this damnatio memoria of Veronese's results. I think that Cantor and Peano had maybe even a personal grudge at Veronese. We shall see this from certain bits from the correspondence. Russell, on the other hand, well, he's guilty of, in a way, uncritically accepting most of the things that were proposed by Cantor and by Peano. And then finally we have Poincaré, who I don't think had anything against Veronese, but he was guilty of this superficial reading, if reading at all, Veronese's book, and then he made two important errors, I believe, which are also present in the history of mathematics even today. So one of the problems with Veronese is that his book is this mixture of mathematics, philosophy, historical analysis as well. So it has this mixture of novel mathematics and what Jeremy Gray calls naive philosophizing. I wouldn't agree that it is naive, but it is philosophizing, certainly. And it was not clearly written. It was not written in the style of Hilbert, nothing of the sort. But this confusion between mathematics and philosophy is, according to some authors, the cause of the lack of clarity. And as Philippe Ehrlich notes, on one hand, we have the ideas of a highly imaginative and profoundly original thinker, and on the other, the ideas that run the gamut from obscure to poorly stated to outright suspicious. So Veronese's style is indeed difficult, but we need to be, I guess, charitable and try to read through the book without making, and approach it without any prejudgments. So the people who tried to do this, there's not that many of them. We have two monographs by Paolo Bussotti and Paola Cantù. Then we have Walter Salvatore Contra in his habilitation thesis from 1968. This was mentioned to me by Sigmund Probst. I didn't know about this. Also, these two papers by René Pfeiffer-Reuter, devoted to Veronese's conception of infinity and his conception of continuity. And as you will see, most of these authors were focused on this non-Archimedean continuum of Veronese, so this theory which is mostly philosophical and less so, I would say, mathematical. And then also here, Gordon Thiessen writing about the Veronese's non-Archimedean continuum, hyperspatial geometry, and then very important papers by Lagwitz and Philipp Ehrlich, I think most extensive discussions of these issues. Interestingly, both Fischer and Ehrlich made promises that they would write longer, more extended studies on the emergence of Archimedean geometry and on Veronese. They haven't fulfilled those promises yet, so there's still quite a bit of work to be done. And I think this was the general consensus also of a workshop devoted specifically to Veronese, which we've organized in Paris at the Institut Henri Poincaré last year. So Paola Cantù, Paolo Bussotti, Victor Pambuchen, Philipp Ehrlich, and myself were speaking about various facets concerning Veronese's theory, and really a lot of work still remains to be done. So to summarize this first bit, expanding well beyond the traditional field, integrating a historical and philosophical approach to these issues, especially detecting lacunas and trying to fill in these gaps in the scholarship, also trying to debunk certain misconceptions or misinterpretations, doing archival research. And this bit here I've added because of these philosophical elements in Veronese. I think it is highly contributional to read through these newer studies in Neo-Aristotelian philosophy of mathematics, because these philosophical bits and pieces that we find in Veronese are unmistakably Aristotelian. So, concerning archival research, I will just mention that Veronese's correspondence with Cantor lasted only for 2 months during 1890, and as Meshkovsky and Nilsson rightly note, Veronese was certainly one of the most intriguing of Cantor's correspondence. Now, the problem is that neither the originals nor copies of these letters by Veronese to Cantor have been preserved. So this means that when trying to reconstruct this discussion and this debate, we have to rely only on Cantor's responses when we are trying to reconstruct what Veronese might have said or responded. But it seems that there are some exciting new prospects. Our colleague Damien Noël-Goose, thanks to his amazing investigative work, had possibly reached a potential gold mine. So where it could be that at least some letters by Veronese to Cantor have been preserved after all. So this will be quite interesting, an interesting find to read through this. So now, the clash with Cantor had to do with Veronese's non-Archimedean variant of the Aristotelian interval-based theory of the continuum and the non-Cantorian theory of infinite numbers. So these numbers which Veronese introduced, he was much, let's say, a supporter of the so-called principles of permanence. So his idea was, okay, I'm introducing this novel kind of numbers in order to provide an arithmetical model of the axioms of my non-Archimedean geometry. But these new numbers, never mind, they might be infinitesimal, they might be infinite, but we shall work with them in exactly the same way as we work with, let's say, regular real numbers. So this was his guiding insight. Of course, as you well know, Cantor was completely opposed to this idea of permanence because he believed that for his transfinite numbers, so the omegas, we need to have a special transfinite arithmetic, so they do not obey all the usual algebraic rules and laws. Interestingly, his clash with Veronese made him produce a so-called proof, an alleged proof against the possibility of infinitesimals, and he distributed this to Benno Carey, to Weierstrass and Goldscheider, and then he reprinted this in the Mitteilungen zum Lehrer von Transfiniten in 1887. And Cantor's proof amounts to the following: infinitesimals are impossible because they contradict the so-called notion of linear magnitude. Now, many interpreters were bashing their brains what this linear magnitude can be and so forth. I believe that if we just read these non-Archimedean authors, such as, for instance, Dubois-Reymond, he speaks of these linear magnitudes, and linear magnitudes in Dubois-Reymond are those which are defined to be they're defined as Archimedean magnitudes. So Cantor's proof actually is circular because he tacitly assumed the Archimedean axiom, and this was demonstrated by Veronese already in the Fundamenti in 1891. It is interesting that also Wilhelm Killing and Russell were insisting that non-Archimedean geometry is not good because we need the axiom of Archimedes because measurement essentially depends upon it. But never mind, these proofs might have not been good, they might have not been adequate, however they made an impression on certain people, and then they contributed to this, what I would call anti-infinitesimalist sentiment. And here it's nice to add this bit on Russell's influence on the reception history of non-Archimedean mathematics, namely in the already mentioned report.
I don't understand. What is the link between infinitesimals and the Archimedean axiom? Because there's no obvious link between them.
Well, because, I mean, when you have the Archimedean axiom, when some given structure, say the ordered field of real numbers is an Archimedean structure, it does not possess neither infinitesimal nor infinite elements. All of its elements are finite. And when you remove the Archimedean axiom, then you can have also infinite and infinitesimal elements of a given structure. So for instance, this non-Archimedean ordered field, which Veronese introduced, it has also infinitesimal stretches, but also infinite stretches within it.
I mean, the p-adic numbers are not Archimedean.
They're also non-Archimedean, yes.
But so how do infinitesimal structures appear naturally if you remove the Archimedean axiom?
But, I mean, they appear as soon as you remove it. I guess. I mean, I'm not sure I get the concern.
Yeah.
Maybe we can, yeah, later on. So the point Russell was making, especially in the principles of mathematics, was that in a way infinitesimals were banished, and that this banishment was given an apparent theoretical urgency. So he was quoting Cantor's authority, mentioning Cantor's proof against infinitesimals, and saying that they were mathematical fictions. So we have this sort of a prejudice against infinitesimals, especially in Cantor, who maintained an unwavering dogmatic opposition to them. And we have several quotes. I won't be going through all of them, but for instance, Vivanti, one of the participants of these debates concerning the status of infinitesimals, goes on to say that infinitesimals are absurd entities, the impossible self-contradictory imaginary entities, as Cantor puts it. They are the cholera bacillus of mathematics, and so forth. Interestingly, Russell goes on to say, infinitesimals as explaining continuity must be regarded as unnecessary, erroneous, and self-contradictory, and a very restricted and mathematically very unimportant conception in general. So, Peano goes on to add, of course, they are sterile and useless, and as Peirce went on to say in his New Elements of Mathematics, the anti-prejudice against infinitely small quantities remains. And this was noted by mathematicians working at the time, for instance by Hobson, and also by historians of mathematics such as Florian Cajori, who goes on to say that Weierstrass's banishment of the infinitely small has found a wide following, and that the infinitesimal, which had been subject of many controversies, was regarded by many as containing an element of mysticism, was banished by Weierstrass and Cantor. And then comes Veronese as a heretic. Heresy had been practiced in the Holy Weierstrassian Empire. Even though we have the school of Weierstrass, it had not found universal recognition, and namely there are modern champions of the infinitely small, chief of among whom is the Italian mathematician Giuseppe Veronese. So Veronese was in a way going against the mainstream. So he was branded as a heretic, as a contrarian, as a counter-modernist in Merton's sense. So he was going against this anti-infinitesimal trend by consistently reintroducing infinitesimals. He was also insisting upon traditional synthetic and intuitive geometry rather than the modern analytic geometry, and he was thus going against the trend of arithmetization. Already in the Fundamenti, he proposed an Aristotelian interval-based theory of the continuum, going against the Cantorian point-based alternative, so this ideas concerning the continuo intuitivo, and in some of his later writings we find traces of Aristotelian philosophy of geometry. I will skip this, and I'll go to this bit here, which is, I think, quite interesting. We have also in Veronese some contrary modernist insights, and this is the perfect pre-Hilbertian style, which we find in Veronese. He goes on to say that abstract axiomatic characterization of the fine structure of the intuitive continuum, as well as subsequent logical treatment and strictly deductive development of geometry, is entirely unaffected by the limitations necessarily imposed by the visual representation thereof. and goes on to add that the axioms, theorems, and proofs must not contain any indeterminate intuitive element, but rather be well-determined. Even though intuition is necessary for the essence of geometry, it mustn't be a necessary element, however useful in the logical development of geometry. So here he was claiming something of the sort which coincides with what Hilbert was saying, that axiomatic grounding of the theory of the continuum is not at all opposed to intuition. So we can have rigor and intuition working side by side, complementary. Also, this idea of mathematical existence, which is typically associated with Hilbert and his Grundlagen, Veronese already articulated it before Hilbert in the Fundamenti, where he goes on to say that mathematical possibility is regulated by the principle of contradiction, namely, mathematically possible hypothesis or an entity is the one which is a consistent one. So, as Jeremy Gray put it, Veronese took the modernist line about mathematics. It dealt with abstract existence, which is simply that the axioms be free from contradiction. Rigor was needed in definitions, postulates, theorems, and proofs, which should be purely abstract, involve nothing indeterminate, and be truly deductive. And finally, we have this very important modernist line in Veronese. This is the study of the independence of axioms, where we see Veronese as a true precursor of the Hilbert style of doing mathematics, where he says that one of the important conditions which geometrical axioms and hypotheses ought to meet in order for geometry to be developed scientifically is that the axioms be independent from one another and not contradicting each other. So, since the Archimedean property of the continuum is merely axiomatic, nothing prevents the consistent development of alternative non-Archimedean systems of magnitudes by mere restriction of the axiom's general validity. And this was the guiding insight behind Veronese's introduction of non-Archimedean geometry. So, finally, I will turn to, I've skipped that bit, sorry, because I want to turn to these misconceptions and misinterpretations of Veronese's book that are particularly due to Poincaré's report on Hilbert's works. And this was Poincaré's actually nomination of Hilbert for the Lobachevsky Prize in Geometry. And he says at one bit that he has to mention Veronese's book on the foundations, in which the author applies Cantor's transfinite numbers in geometry for the first time. And then similarly to Poincaré, other mathematicians, including Cantor himself, go on misidentifying Veronese's numbers with Cantor's transfinite ordinals. So we find this in Peano, in Vivanti, in Killing, Schoenflies, and many others. And then this results, from a historical perspective, with something quite peculiar, that Veronese starts being seen as Cantor's follower, which he obviously was not. The question then arises, have these people actually read Veronese? Because as you see here, here, Veronese says in one of the paragraphs of the Fundamenti, we mark this paragraph with an asterisk because no use whatsoever is made of Cantor's transfinite numbers in the foundations of geometry. And not even in this introduction, but for the sole purpose of comparison with our own finite numbers. I have explicitly noted time and again that my infinite and infinitesimal numbers are of an altogether different nature than those of Mr. Cantor. And this was obvious, interestingly, to Branislav Petronijević. No wonder Veronese then considered him one of a handful of people who understood the theory properly. Interestingly, Cantor believed that Veronese's numbers are only tenable if they are identified with his own transfinite numbers. But the main issue with Veronese here is that Cantor believed that his theory of infinity, actually, was the right one and the only admissible one. Of course, another inadmissible idea for Cantor was the reintroduction and rehabilitation of infinitesimals. And when we see that Veronese had produced one of the most elaborate non-Archimedean theories of the 1890s, he naturally becomes a natural target of Cantor's attacks. And as Joseph Dalton says, to accept the work of Veronese was to deny perfection of Cantor's own creation. Understandably, he launched a thorough campaign to discredit Veronese's work as vigorously as he could. I won't be reading through all of this again, but you see this correspondence. Veronese's work is labeled as flights of fancy, that his and Cantor's theory cannot both be true. He also refers to his own alleged proof against the possibility of infinitesimals in this context. He says that his hope on converting Veronese to the truth in this unfortunate matter disappears completely, and that false theories do not become true by repeating or varying them. And then, that what Veronese says is fantasies. His conclusions are not scientifically justified. The mathematical basis of Veronese's work is absurd, And then we have this review by Peano of Veronese's main book, where he says that it would be possible to continue enumerating all the absurdities which the author has piled on, but these errors, lack of precision and rigor from the entire book render it completely worthless. Tolgono adesso ogni valore. So Veronese is not the man to be writing on the foundations of geometry. That's the first error. The other misconception, and this is the final bit, is this peculiar situation when now we start looking at Veronese as Hilbert's notable follower, because in the same report, Poincaré goes on to say that non-Archimedean geometry is Hilbert's most original conception, and that Veronese merely had an analogous idea in which Cantor's stress finite numbers play a dominant role, which obviously is not true. So Hilbert has really made the new geometry his own. And then the question, of course, arises, who introduced non-Archimedean geometry? Was it Veronese? Was it Hilbert? Veronese felt the need to address the issue in this paper concerning this priority dispute. And then we have also this case of the missing footnote from Hilbert's Grundlagen der Geometrie, in which Hilbert, initially, in the first edition, we have this footnote where he says that Veronese had tried to set up a geometry independent of the Archimedean axiom, and he refers explicitly to Veronese's results prior to his own, but then this footnote then later on disappears. What is interesting, I can't go into this slide right now, it might be the case that it was a certain letter passed on by Friedrich Schur to Felix Klein, and then from Felix Klein to Hilbert, which actually inspired Hilbert to start lecturing on the foundations of geometry, and these investigations into the independence of the Archimedean axiom is very prominent, so it's definitely the case that Hilbert was relying on Veronese when writing the Grundlagen. And these Poincaré-style misconceptions, I believe, had devastating consequences for the reception history of Veronese's theory. And I will just give you two examples from contemporary literature. One is Gerd Schübring, the other Jeremy Gray. Gerd Schübring says that an impressive example of this developmental stage where geometry remained a field where non-Archimedean objects can be made concrete was Hilbert's Grundlagen. And then on the other hand, we have Jeremy Gray saying that only Hilbert took seriously the question of how geometry would fare in the presence of the or absence of the Archimedean axiom, and then also adds that the Italians' work was limited because they missed the potential for creating novel geometries, and that they failed to see the broader significance of the axiomatic method. So novel geometries and research were not on the agenda. I believe that such conclusions are not that well based, and that they can be challenged through, of course, historical scholarship. So are these pessimistic conclusions okay? So Veronese's approach did not have any substantial effect. His contribution has been all but forgotten. It sank into relative obscurity, and his influence appears to have been minimal. I believe we need not be as pessimistic, that we can be optimistic, but that just means that a lot of work still remains to be done, and I hope I've given you at least some clues as to how this may be put forward. So thank you very much.
Thank you. We have a few minutes for questions. Go ahead, Frederick.
Yeah, thank you very much for this very rich talk. So I wondered about the stages of Veronese's work in its reception before the 1920s, at the time when it's very much discussed, because we've seen many reviews, reports, discussions in correspondences, and so on. So is it mainly in these kinds of discussions that actually Veronese's work is considered, or is it also in mathematical papers solving problems, these kind of things?
So, I mean, we have both things actually in this period prior to the 1920s. Some people are referring to Veronese's results and then employing them in their own work, so producing novel research. This especially holds for these people working on non-Archimedean theories of magnitude. So Levi-Civita, Hans Hahn in his on non-Archimedean ordered systems of magnitudes. We have people like Otto Hölder, for instance, and many others. And then on the other hand, we have these reviews. Then we have these polemical, let's say, papers in which people criticize certain points of Veronese's theories, but I believe most of these criticisms actually do rely on some sorts of misinterpretations, such as these which are found in Poincaré's work as well.
As far as Hilbert's Grundlagen der Geometrie and Veronese is concerned, I mean, Hilbert's Grundlagen were not written like this. I mean, he has taught at least 2 courses beforehand, and they exist. I mean, there are.
Yes.
Have you checked that whether Veronese appears?
I've checked it, and I honestly can't remember whether he appears or not. But I remember that
But
people,
you checked it, right?
yes, but I remember people writing on this genesis of Hilbert's Grundlagen, that especially focus on this letter, because they think that it was this provided the crucial, let's say, incentive for Hilbert to get into the study of the independence of axioms.
Ah, interesting.
Mhm.
Okay.
Go ahead.
Yeah, I just have something speculative, which is this strange confusion there between transfinite and infinitesimal. Does it not have something to do with the construction of the completion? Because you know, when you, for instance, when you construct the p-adic numbers, you complete Q with respect to the p-adic.
Yes.
And that then, of course, leads to something which has the power of the continuum. And it's around the same time that QP was defined by Hensel.
True.
Just around that.
Indeed.
So, is that maybe where the
I think it might have something to do with it, actually, because, I mean, when people like, for instance, Hans Hahn, 1907, these results on Non-Archimedean ordered systems, I mean, when people started focusing on issues such as completion, for instance, of fields and stuff like that, or embeddings of certain structures once within some other ones, then these issues started getting resolved. So we started getting these more precise, clear-cut ideas of what these numbers are, how are they to be employed, what are they useful for, and so forth. So it definitely has something to do with it.
Do we have anyone else? A question this morning? Right, seeing none, we'll thank you again for your questions.